So we're going to switch gears now and maybe try to take geopolitics out of the equation a little bit. I'm going to give a little bit of a, let's say, technology overview of technological solutions, some of the things that we're trying to do with a range of different collaborators in the US and in Israel, thinking about water treatment challenges and resource recovery challenges. So we're moving a little bit away from water resource management, especially at the basin scale, large scale, and certainly out of geopolitics, although it's difficult to remove geopolitics from the equation, of course. So what I want to talk about is a little bit of the work that we're doing towards a sustainable and circular water economy. By the way, I guess I should introduce myself again. I'm George Wells. I'm an associate professor of environmental engineering here at Northwestern, and I specialize in environmental biotechnology and microbial ecology. So putting microbes to work to clean water and recover resources, which is exactly what we're going to talk about. I'm going to focus in on some collaborative advances at the Water Energy Nexus in a center that we have here at Northwestern. It's actually co-directed with Ben-Gurion University in Israel. Hopefully we can talk about ways to maybe expand this type of research to other areas in the Middle East as well. So a little bit of a roadmap here. I want to talk about water circularity, the Water Energy Nexus, just a bit, lay the groundwork a little bit. I'm going to focus in on some of the technological solutions that we're evaluating as part of the US-Israel Collaborative Water Energy Center, or COWORK. And then at the very end of my talk, I'm going to try to make a pitch or, let's say, discussion points, and I'd love to get some input on this, for the fact that I think there are key opportunities to expand healthy interdependencies. I like this term that Fred used yesterday, healthy interdependencies, not just for water implementation, water technology implementation, but also for research. And I think there's a lot more that we can do on that front. So a little bit of a groundwork here, a little bit of a framework. In many parts of the world, our water management in urban systems relies on what I would call an outdated 20th century paradigm. That paradigm is designed for linearity, for separation. A bedrock principle of environmental engineering is separate drinking water from wastewater. Of course, this is something that we're reevaluating in many parts of the world now. For uniformity, meaning use of essentially the same types of processes in most parts of the world, most cities, with little alteration based on local conditions, and extreme centralization, right? So thinking about decentralized treatment and water reuse versus centralized treatment and water reuse. Just a bit of a schematic of very high level way that we manage water in cities. At present, we have just a couple of really high quality water sources that we typically turn to, surface waters and groundwaters. We subject these to relatively old technologies that work okay for removal of conventional contaminants from water, but they use massive amounts of chemicals. Those chemicals are generally sourced via fossil fuel-based production processes. They produce massive volumes of waste, residuals that we have to manage. We produce high-quality water, drinking water quality water in municipal drinking water treatment plants, but most of the water that is used in society is not drinking water, right? So thinking about fit-for-purpose water treatment rather than treating everything to drinking water quality. This is something that is of great interest. And then these processes tend to be fairly energy intensive. We use that water in urban systems or industrial systems and the like. The water quality inevitably degrades a little bit, but we still have primarily water in what we call wastewater. We subject that to primarily some physical, chemical, and some biological processes that are extremely energy intensive. They're also prone to production of greenhouse gas emissions like methane and nitrous oxide. These non-CO2 greenhouse gas emissions are quite relevant and quite important for the water sector. And again, we produce high volumes of residuals here as well. And in most parts of the world, outside of Israel and a handful of other places, we release that water to a receiving water body, which certainly has environmental benefits or can have environmental benefits. Can have environmental, certainly impacts as well, given the fact that we really only are good at removing conventional contaminants from water at this point. There's a lot of work to be done looking at emerging contaminants. I want to zoom in on wastewater treatment in particular because that's kind of my, let's say, bread and butter. I think a lot about biological treatments for wastewater treatment, water resource recovery. By the way, I don't like the term wastewater. I have used water in parentheses here. I think somebody mentioned Singapore. yesterday. Singapore uses the term used water in place of wastewater, which I think is an extremely important semantic reframing. It's not a waste, it's just slightly used, lightly used water that we can consider for reuse. So conventional wastewater treatment plants are highly energy and resource intensive. If we look at where that energy is actually used in conventional treatment processes, most of it is used to supply oxygen for microbial activity, for aerobic microbial activity. We're basically supplying oxygen to convert reduced organic carbon contaminants in wastewater into carbon dioxide. So massive amounts of oxygen, average around 50%. This can be up to around 80% of energy use in a wastewater treatment plant. And that's important because wastewater treatment overall accounts for a fairly significant percentage of overall energy use. In the US, this accounts for about 3% of nationwide electricity use. That's equivalent to about 15 gigawatts of power. And this is a bit paradoxical because when we look at the energy potential in organic carbon, in particular in wastewater, there's a lot of energy there. There's a lot of energy. If we look at the total energy potential in organic carbon in the US in industrial, municipal, and agricultural wastewater, the estimate is that there's potential energy equivalent to about 17 gigawatts of power. So there's a clear opportunity here to move from an energy intensive sector to an potentially energy neutral, or maybe even in some cases energy positive water sector. And that really underlies much of what I think about in my group, much of the, let's say, direction of our field, which is a shift towards resource recovery, a paradigm shift, I would say, in the way that we view waste streams as a whole in society. Just a bit of a schematic of very high level what this looks like. Here's our current processing paradigm for wastewater in urban systems. We have high organic matter, high nutrients in wastewater. We send these to highly centralized wastewater treatment plants, expend a fair bit of energy and money. We do a decent job of removing conventional contaminants like nutrients, total suspended solids, and organic carbon, produce fairly clean water, and in most parts of the world, we then release that to a receiving water body. This is a case of what's been termed misplaced resources. The organic matter in wastewater, the nutrients in wastewater, and of course the water in wastewater all have value, and it behooves us to think about ways to shift towards a circular water economy and energy positive water resource recovery facilities by rerouting these misplaced resources and closing the engineered water cycle. So just a little bit of a high-level schematic of what we think this might look like. Very high level. We take used water, not wastewater, just used water. We route it to what I like to call integrated urban biorefineries. Doesn't have to be urban, doesn't have to be bio, but typically bio is cheaper, less energy intensive, and easier to operate than other processes. So I will argue in favor of biological treatments, where we seek to extract energy, extract nutrients for fertilizer production, for example. Maybe we can produce bio-based materials from that organic carbon. Maybe we can produce platform chemicals, bio-based platform chemicals for that organic carbon as well. And of course, we also produce clean water, and where it makes sense, we route that for reuse. In the Middle East and in Israel, that makes a lot of sense, although we can have some debate about environmental impacts as well. One of the interesting questions that I would love to discuss further is drivers for water reuse in water-rich areas of the world, like Chicago as well, because that's a little bit of a harder argument to make, I think. So key drivers for technological innovation in the water sector, at least in my general field, this move towards water and resource circularity at the water-energy nexus. I'm going to expand that a bit and add food in because we have nutrients and water reuse for agriculture and the like. Moving towards decarbonized water systems, limiting greenhouse gas production, carbon consumption, and what some might term climate-independent water sources, which is a little bit of an interesting term. There's a little bit of tension here because a climate-independent water source might be something like desalination of seawater, which is carbon intensive. The water source may be climate independent, but the processing scheme might be carbon intensive. So there's a little bit of tension there. Wastewater and saline groundwater, as well as sort of alternative water sources. And then finally, a key driver is mitigation of emerging contaminants or contaminants of emerging concern. Key among these are so-called micropollutants, which are very diverse. These are contaminants that are present in very low quantities, and most of the water bodies on Earth now. So it's a couple of key examples that folks in our center are looking at are fluorinated chemicals, PFAS chemicals, so-called forever chemicals, pharmaceuticals, personal care products, and the like. These are often present at extremely low concentrations, and oftentimes we don't have a complete understanding of the potential impact to environmental health or to public health. We also don't have, let's say, appropriate technologies at present to really manage these micropollutants in water. So I want to make the point that technological innovation has really changed the landscape. This is a little bit of a repetition from what we've seen already, but I'd like to look at the adoption of new technologies in Israel over time. And what's really astonishing to me is how rapid the shift has been in Israel. We're looking at really this new water source that has been a game changer in Israel and many other parts of the world via seawater-based reverse desalination with reverse osmosis membranes. We can see on the x-axis we have year, on the y-axis we have the total supply in millions of cubic meters per year. If we go back about, let's say, less than 20 years or so, there's only a very small amount of water that is being supplied in Israel via seawater reverse osmosis. The first large-scale desalination facility was opened in Ashkelon in 2005, and you can see that there's been an enormous increase in production since that time at present. More than 650 million cubic meters per year of fresh water is produced in Israel by desalination, and 75 to 80% of home water use is supplied via seawater desalination. That's within 15 years. That's an amazingly rapid change in the water sector. The water sector is historically an extremely slow-moving sector. It does not move fast in terms of technology adoption. So this is really, really quite an amazing shift. We also see this in terms of wastewater reuse. We're looking at agricultural water consumption in Israel starting in 1960 and then projected out to 1950. And the really amazing thing to me here is the shift in agricultural water consumption from conventional freshwater resources, which here is termed potable, but this is really freshwater resources. Then starting in the early 1990s, the shift over to wastewater effluent, which now accounts for a quite substantial, about 40% or so of agricultural water consumption in Israel. Overall, Israel recycles about 90% of its municipal wastewater, which is by far the highest of any country in the world. The second most highest percentage is Spain, which is around 20% or so. So massive differential between wastewater reuse in Israel and the rest of the world. So those are examples, I think, of some implementations of novel water technologies that have really changed the landscape in Israel and are changing the landscape in other parts of the world, in the Middle East at present. Of course, there are negatives that go along with that as well, which would be interesting to chat about. But I want to talk about some of the areas for improvement, let's say, and there are many, in terms of our management of water in urban and agricultural systems as well. In particular, I want to focus in on some of the work that we're doing in a center that started about 2 years ago, the Israel-US Collaborative Water Energy Research Center, or COWORK. COWORK is directed by my colleague Aaron Packman, who unfortunately is not able to be here today, but he is the co-organizer of this symposium. And then in Israel, we have a co-director, Moshe Hertzberg, at Ben-Gurion University. There are 2 other universities involved, Yale University here in the US, and then the Technion in Israel as well. We have a range of different water utilities, wastewater utilities, and companies that are also key partners in this effort. COWORK's mission is to leverage recent advances in both the US and Israel to reduce the energy intensity and the cost of water across the water spectrum. The approach to doing this is to guide development and testing of new technologies using energy systems, energy water systems analysis, and incorporating new understanding of both materials and processes, including bioprocesses, microbial processes, to improve a number of different areas. There's a key focus on energy-efficient enhanced water supply via desalination, wastewater reuse, and resource recovery. Then we have this sort of umbrella theme of integrated energy water systems that covers all of these areas. There's a lot of activity, a lot of people involved in this center. I'll just give you a brief overview of the 6 main overarching projects as part of this center. The first, within water supply, we have high recovery ion selective desalination. This includes electrochemical approaches, as well as innovations in reverse osmosis or membrane treatment. We also have development of novel materials, in particular fouling. Fouling is a major problem still in reverse osmosis and really any type of membrane treatment for water. On the resource recovery side and wastewater reuse, we have a major focus on biotechnologies for nutrient and energy recovery. We also have a major focus on efficient trace organic pollutant removal. What do we do with those micropollutants in water? How do we manage those? And then finally, on the energy water system side, we have a focus on low energy water reuse using approaches like soil aquifer treatment, so kind of more nature-based solutions, and then a systems analysis focus that couples techno-economic analysis and life cycle assessment to really understand the impact overall of the technologies that we're focusing on. I don't have a huge amount of time, so I just want to introduce you at high level. I also realize that I'm one of the few engineers in the room, so I'm not going to get into a huge amount of detail, technical detail here, but I'll give you just a little bit of a profile of some of the approaches that we're looking at in my area of interest, which is biotechnology for nutrient and energy recovery. One of the primary areas that we're evaluating in Israel is a novel approach to energy extraction from wastewater. This is using what's called an anaerobic membrane bioreactor. The key idea here is that we have used water that's high in reduced organic carbon. I like to call this negative value carbon because people will pay you to take it. It's a feedstock to a process where we can produce clean water, but we can also potentially produce energy. And we can use anaerobic microbial consortia to do this. We can produce biomethane that is substitutable directly, renewable methane, for natural gas. So it's a way to potentially substitute fossil fuel consumption with microbially produced bioenergy directly extracted from waste organics in wastewater. So there's a major focus on this in Israel. It's at Ben Gurion University. Here's a pilot scale test at the Shafdan wastewater treatment plants just outside of Tel Aviv. There's a number of different lab scale systems as well. By the way, one of the key areas of focus in this center is not just development of widgets in the lab. We want to take technology, test it in the lab, and then push it up the technology readiness level scale, meaning pilot scale testing and full scale testing. And we can see that pilot scale testing here. We produce low organics but high nutrient water out of this process, although there's still quite a bit of work to be done to develop this process. But that's the ideal case. This is potentially a good feedstock for irrigation, either in urban agriculture or in agricultural fields, if we're able to use those nutrients directly for fertigation, fertilization, and irrigation. But in many parts of the world, that's quite tricky. In Chicago, for example, if we were to use a process like this, we have a growing season that's only 6 months of the year. What do we do for 6 months of the year? Also, our agriculture is really far from the center of the city. So transportation of water with nutrients in it is quite challenging, quite energy intensive. So we're also thinking about ways of recovering those nutrients from water, removing the nutrients from water, recovering them as fertilizer or as value-added products. I'm just going to mention one technology module that we're looking at in my group, which is a microbial bioprocess. We use a mixed culture microbiome in what we call the CANDU plus P microbial bioprocess. The key goal is to take nutrient-laden water, convert it into a bioenergy molecule that we can completely capture, nitrous oxide, and clean water. And we're also aiming for phosphorus recovery as fertilizer as well. I just want to lay the groundwork, just a little bit of a case study into this potential technology. I want to emphasize this is fairly low on the technology readiness level scale. So this is a bit of a blue sky lab-based process, but we think it's potentially an interesting way to think about resource recovery and sustainable wastewater treatment. So here's the basic idea. We're going to focus in on a very interesting molecule, N2O. N2O is actually a natural component of the atmosphere. Pre-industrial times, concentration of nitrous oxide N2O was about 270 ppb. At present, it's up around 334 ppb or so. So you can see this clear increase in nitrous oxide over time. And that's interesting and important and alarming because nitrous oxide is a very potent greenhouse gas. It has a global warming potential about 3 to 10 times that of carbon dioxide. It accounts for about 8% of worldwide greenhouse gas emissions. Where does that nitrous oxide actually come from? There's a range of different sources. One of those sources is wastewater management. Where does nitrous oxide come from in wastewater management? It comes from the microbes in biological processes. A number of different microbial pathways for nitrous oxide production. This is the only chemistry I'm showing in this presentation, so don't worry. We'll look at just a basic pathway for one of these microbial groups, functional groups that we use in microbial bioprocesses called denitrification. Here's the basic idea. In denitrification, we try to take nitrate, NO3-, in water. That's not something we generally want to release to receiving water bodies. We want to convert that generally into nitrogen gas. The atmosphere around us is 79% nitrogen gas. So we're basically putting it back in the atmosphere. But that denitrification process proceeds through a series of intermediates, including this one right here, which is nitrous oxide, that potent greenhouse gas. And under some conditions, this last step in denitrification can be inhibited, leading to high emissions of nitrous oxide. So I just mentioned, of course, nitrous oxide. It's a very potent greenhouse gas. It's something that we and many other groups are seeking to understand mechanisms of production for and means to mitigate those emissions, right? That is the key goal in most engineered and impacted natural environments at present. But with collaborators, we've also realized that N2O is a powerful potential bioenergy molecule. It's used, for example, in rocket engines as a monopropellant in rocket engines. It's also used as an energy booster in race car injection engines and in sports cars, right? So it's an energy-dense molecule. So a little bit of a flip side of N2O here. And so with this in mind, we've developed an integrated process that we call the coupled aerobic anoxic nitrous decomposition operation, which is a mouthful of a name, but we like the acronym. It's the CANDO process. We like to be very positive with our bioprocess names, where our intent here is to develop a resource-efficient, microbially driven route for nutrient removal from water, producing clean water, but then capture of that produced nitrous oxide as an energy source. And of course, if we capture the nitrous oxide, we also prevent fugitive emissions, at least theoretically. That's a very important point that we're focusing on. In recent years, we've expanded this, or in the co-work center in particular, we've expanded this to couple that goal of nitrogen removal and bioenergy production with the goal of also capturing phosphorus in wastewater in a form that can be used fairly readily as a fertilizer. So kind of trying to circularize that flow of phosphorus in wastewater as well. We do this with a particular type of microbe. I won't go into detail about this class of bacteria called polyphosphate accumulating organisms. And I have to show just a little bit of data from this just to convince you that we can actually produce nitrous oxide in this system. This is just a lab scale system at present, not scaled up. But here we're looking at just one particular cycle in this reactor. And we have about 3.5 or 4 hours or so of time on the x-axis. We have hundreds of cycles that look like this, so I'm just showing you a representative cycle. On the y-axis, we're looking at a couple of different nitrogenous species. We have our waste nitrogen, that's nitrite here, we feed into the reactor. You see rapid drawdown of that pink line, and then that nitrite is converted, removed from water and converted quite efficiently into this green line here, which is nitrous oxide. Here we're seeing about 70 to 80% conversion of reactive nitrogen to nitrous oxide as a novel bioenergy molecule. So again, this is I would say a blue sky idea. It's relatively low on the technology readiness level scale, but we're interested in this and we think this is intriguing because it may be a way to rethink what is a waste and what is a resource, while at the same time alleviating greenhouse gas emissions. If we can completely capture nitrous oxide and then use that as an energy source, that should, at least theoretically, eliminate fugitive emissions of nitrous oxide. So the last 2 to 3 minutes of my talk, I'm going to switch gears away from co-work, and I just want to, it's really a way of starting a conversation. I want to start a bit of a conversation around ways of using research, water technology research, as the basis for collaboration, maybe apolitical collaboration between Israel, Palestine, and the Middle East. And I'm going to focus actually here just a little bit. I'm going to echo a little bit of what David said yesterday. I guess I should have compared slides before I put these together. But the situation in Gaza is really quite interesting, I think, as an illustration of potential opportunities for healthy interdependencies. I like this term, healthy interdependencies. This is a picture actually of our global engineering trek to Israel last September, led by Eli Rekes, and I was the, let's say, sous chef on this trip, the assistant lead on this trip. And we took a group of 16 undergraduate students on a 10-day trip to Israel. We visited a range of different water-related sites, historic and modern. This is one of the last days of our trip where we sat down with folks from 𝐒𝐞𝐯, which is an amazing organization really working at that boundary between environmental issues at the boundary between Israel, Palestine, and Jordan. One of the things that we talked about here was this conflict or this disparity, let's say, in water between Israel and Gaza. So here, of course, is our map of Israel. We have Ashkelon right here, which is the site of that first large-scale water desalination facility, 108,000 meters cubed per year of fresh water, one of the most advanced water supply facilities in the world. And if I measure the distance from Ashkelon to the border with Gaza, on Google Maps, it's about 3.5 miles or so from Ashkelon to Gaza, the border with Gaza. And Gaza, as we've heard already, is in the midst of a severe, I would call it, water crisis. It's one of the densest populated areas on Earth. There's a severe shortage of safe drinking water and of sanitation. So minuscule distances, at least from a U.S. standpoint. Maybe it's not so minuscule from an Israeli standpoint. From a U.S. standpoint, 3.5 miles, very, very short, but very stark differences in water outcomes. And as was mentioned yesterday, only a tiny fraction of the domestic water supply in Gaza is fit for human consumption. Much of that is due to there's salinity in the water, but also nutrient pollution. So some of the same nitrogen pollution that we were just talking about. Managing, here we're looking at nitrate values in groundwater, and these are just astonishingly high nitrate concentrations, really kind of unbelievably high nitrate concentrations. There is, as David mentioned, this very interesting connection, maybe a bit of self-interest for both Israel and Gaza to solve this problem in terms of the fact that they're very close together. So pollution or water issues in Gaza have a clear impact on water issues in Israel, particularly via polluted water, runoff or wastewater effluent, making its way into the Mediterranean Sea, which of course is the water source for the Ashkelon desalination facility. So here I'm focusing on potential opportunities for collaborative water technology implementation. I also want to emphasize there's an opportunity for smaller scale research collaboration as well, which I would be really interested in trying to flesh out and explore a bit more. So I think I need to wrap up. I'm going to give you a couple of takeaway points. Hopefully I've convinced you that innovations in water technology are a piece of the puzzle. They're certainly not anywhere near all of the puzzle, but a piece of the puzzle in transitioning to a circular and sustainable water economy in Israel, the Middle East, and beyond. We talked a bit about energy, nutrient, and water recovery and reuse, decarbonized water systems, and then non-traditional water sources, moving away from this dependence on just high quality water sources. And the last thing I mentioned, of course, was this potential opportunity for transboundary water technology research and implementation. And I'd like to thank you for your attention. I'll take any questions. Yes, Julie. Yeah, thank you.
Thank you very much. My first master's was in chemistry, so I especially enjoyed your talk.
Great.
And I was wondering, do you already have a collaborator in Gaza?
I don't.
Okay,
no.
𝐒𝐚𝐿, Islamic University of Gaza.
Perfect.
He's your man.
Yep.
You
That's
really have
great.
to email him today.
Wonderful.
He will,
Okay.
he'll be on this with
I
you
love
immediately.
It. That's wonderful. Okay. That's
Really, before 24 hours, you have started something here.
That's terrific. That's wonderful. Thank you for that.
Hi, thanks. I don't have a degree in chemistry. I don't understand chemistry. But what I'd like to ask is, in Israel, you mentioned Shafdan and these big places, wastewater treatment centers. In Israel, everything's very centralized, but as Julie said, in the West Bank and Gaza, it's very decentralized. And how much of what you're working on is implementable at a local scale? So you could decentralize treatment, which would actually be quite efficient and wouldn't necessitate all this collaboration between partners and countries. One of the things they're looking at is how to do sort of local scale wastewater treatment.
Right. Yeah.
So my question is, decentralized
absolutely.
systems.
There's a very strong argument in favor of decentralized wastewater treatment, particularly when it's coupled with decentralized water reuse. And there are a range of very interesting technology options. These particular technologies that I introduced today, in the form that I showed today, are probably not applicable to this. But with slight twists, for example, anaerobic treatment. Anaerobic treatment can be implemented in very simple forms at household scale. So that is possible. I worry a bit about you're producing methane, so fugitive methane emissions from small-scale systems. I think that's a bit of a concern, but it absolutely can be translated to appropriate technologies for decentralized systems. The other thing that I'll just mention is there's a whole range of very interesting technologies that I would call nature-based solutions. Things like constructed wetlands and the like that can be implemented also at small scale and could be appropriate for some of these decentralized treatment approaches too. Yeah, very good question. Yeah.
Hi, Professor Wells. Is there any work that you've done here locally that you've extended back to Israel or some reciprocal action from local work at MWRD, for example, that you've presented to Israel?
Yeah. So that's a good question. The end goal of the Can Do Plus P process is pilot scale testing together with folks in Israel. We're also looking at, probably in the next year or two, there's some work on novel sorbents for phosphorus removal and recovery being developed in Israel that we're going to hopefully test here in Chicago as well. Yep, that's a really good question.
Hi, my educational background is in chemistry and philosophy,
Great.
so I really enjoyed that little injection of chemistry in it. There are some low-key efforts to bring scientists from the region together for quiet conversations.
Yeah.
They don't want to be high-profile because the nation-states get nervous about these things, but have you ever been approached to come and give a talk or come and meet some colleagues from the region without getting too specific about it?
Yeah, so it's interesting for a researcher interested in water. Every country in the Middle East is interesting, right? And so I have built collaborations with folks in Egypt, folks in Saudi Arabia, and in Israel. But bridging between those is, I don't know how to do that. That's something I would be really interested in exploring. The other thing I'll mention is there is an Arab American Frontiers in Engineering conference that happens every year that includes, it's about 50% US scientists and engineers, and about 50% scientists and engineers from across the Arab world, including Palestine, but not Israel. Israel is not included in this conference, which I think is a missed opportunity to use what should be an apolitical topic, which could be water technologies, to bring together researchers. So the answer is yes, I would enjoy more connections, and I have connections to a number of countries in the region, but bridging between those is really the difficult part, or at least I don't know how to do that. Yeah, that's a good question. Yeah.
Yeah, Israel has a limited coastline, obviously, on the Mediterranean. How much further scalable is the desalinization approach in Israel, and is it economically viable? What's the cost of that water? For example, why is there no desalinization plant being planned, or maybe there is one in Gaza?
I think I would probably have to defer to David or Julie to answer this. Folks more on the economy side. 50 years, you said.
50 years, that was 20 years ago. 30 years.
Yeah,
So it's
yeah.
30 years left now.
Yeah.
Don't call that long-term sustainability.
Yeah. Right, exactly. Although, so certainly Israel has kind of gone all in on desalination, and some other parts of the world are doing this as well. And so, is it economical? Well, I'm going to let the economist answer that question.
Can you use the mic? Sorry.
It's economical for Israel for drinking water for municipal purposes because it's a rich country. It's a high willingness to pay. It's questionable whether it's economical for other uses, certainly for agriculture or other uses. But it is the main strategy that Israel has. In terms of the limited coastline, yeah, it does take up coastal space. They're working on now making desalination plants that are inland, so you would pump it in a bit. There's obviously a risk of doing that a little bit with polluting the coastal aquifer if there's some kind of leaks. And I had a committee who was fond of saying it's not a question of when things or if things break, it's a question of when they break. And so, there's always risks with this, but the risks to the aquifer of not desalinating are over-extracting and seawater intrusion, which are questionably or arguably bigger risks. So.
And not being an economist, I'll add two things that I think I find intriguing. One is the idea that the cost of water, the way that we should view the cost of water in urban settings in particular, probably agriculture as well, is not just the cost of supplying the water, it's really the cost of running out of that water. If we have a drought or the like, what is the cost of not having that water? The other concept that I like that we haven't talked too much about, you mentioned conservation, right? So this concept of the cheapest new water supply is to reduce your water demand, negaliters. I love this term, negaliters. Instead of adding megaliters of water, if you can add negaliters of water, negative liters of water, and that's something we haven't talked too much about. Yeah.
Julie. It's just to bounce back on what you've just said. For example, if you simply change your parking lots from a macadam surface to a gravel surface, you've increased significantly the amount of rain that will seep into the ground instead of just run off on an impermeable surface. So you have very cheap things that you can do that will reduce, actually increase the quantity of water in the soil and thereby reduce your demand for imported water.
Several years back, I came across this Israeli startup that was it was like a pooper scooper that you dropped a phosphorus tablet in there and would instantly turn the feces into fertilizer. And I don't know what happened to the company since then, but got me thinking. I'm just wondering, piggybacking off of that earlier question, is there a way to move this type of technology into the home where you're either doing filtering or purifying some of the water up front so that it eliminates a lot of the high energy costs towards the end? And separately from that, how is AI being used now to conserve or make energy more efficient, at the local level or otherwise?
Yep, so very good questions. So on your first point, there are some really interesting approaches for highly decentralized recovery of fertilizer or of energy, anaerobic processes at small scale, as I mentioned. But also, there are these composting toilets that have been used for decades, right? These are very interesting ways to have a simple, decentralized system. The result, it's not energy, but you can get nutrients out of that. You can reuse it as a fertilizer. So that's a really interesting kind of low-tech option. The AI side, so when we think about robust treatment, especially in dense cities at decentralized scales, automation, sensing, and control are huge issues, right? That's one of the key reasons that these are not feasible. It's also one of the key reasons we use so much energy, because we over-design these systems because we don't want them to fail, and we have very high safety factors in them, right? So I think data-driven sensing and control has the potential to play a key role in decentralized treatment. The MWRD and many other utilities are really interested in what's called digital water. That's large scale. That's not necessarily small scale, but there's a lot of potential there. Yeah. Oh, yeah. So exactly. Sensing of leaks, for example, in distribution systems. Sensing in general. Yep, absolutely.